In the quiet darkness between galaxies, something ancient and enormous is waking up. Far from the light of any star, in regions of space so vast that the human mind can barely hold their scale, clouds of gas and dust have been gathering for millions of years. They drift in silence, these cosmic nurseries, waiting for the moment when gravity whispers just loudly enough to begin something extraordinary. Tonight, we will travel into the hearts of nebulae, those immense and luminous cathedrals of creation, where stars are born in slow, magnificent silence. Welcome to Let's Learn While You Sleep. Tonight, let the weight of the day fall away from your shoulders and allow yourself to drift upward, past the rooftops, past the clouds, past the thin blue veil of our atmosphere, and out into the boundless ocean of space. We are going somewhere very old and very beautiful. We are going to the places where stars begin. A nebula is not a single thing. It is a landscape, a territory of space that can stretch across light years, filled with hydrogen, helium, and traces of heavier elements, all swirling together in patterns shaped by gravity, radiation, and time. Some nebulae are the remnants of stars that have already died. Others are vast reservoirs of raw material, untouched and patient, waiting for the conditions that will ignite new suns. In the pages of this cosmic story, creation and destruction are not opposites. They are partners, dancing together across billions of years. So settle in, breathe slowly, and let us begin at the very beginning, with the simplest substance in the universe and the longest patience imaginable. To understand how a star is born, we must first understand the raw material from which all stars are made, and that material, remarkably, is almost nothing. Hydrogen is the simplest element in existence, a single proton orbited by a single electron. It is the most abundant substance in the known universe, comprising roughly 75% of all normal matter by mass. Helium accounts for most of the rest, around 24%, with all the heavier elements, carbon, oxygen, iron, gold, making up barely 1 or 2% of the cosmic inventory. These elements did not always exist. In the first few minutes after the Big Bang, approximately 13.8 billion years ago, the universe was a blinding maelstrom of energy, too hot and too dense for atoms to form. But as space expanded and cooled, protons and neutrons began to combine. Within the first 20 minutes, the process known as Big Bang nucleosynthesis produced hydrogen, helium, and trace amounts of lithium and deuterium. That was all. No carbon, no oxygen, no silicon or iron. Just the lightest, simplest atoms scattered across a universe that was still unimaginably young. Over hundreds of millions of years, this primordial gas drifted and pooled under the gentle influence of gravity. In regions where the gas was slightly denser than its surroundings, perhaps by only a fraction of a percent, gravity gained a small advantage, pulling more material inward, which in turn made the region denser still. This is the principle of gravitational collapse, one of the most fundamental processes in astrophysics. It is extraordinarily slow, it is extraordinarily patient, and it is the engine that drives the birth of every star that has ever shone. These accumulations of hydrogen and helium, stretched across light years, are what we call molecular clouds, or sometimes giant molecular clouds when they span hundreds of light years and contain enough mass to form thousands of stars. They are cold, often just 10 to 20 kelvins above absolute zero, and they are dark because the dust mixed within them blocks the light of stars behind. They are the quiet cradles of the cosmos, and they hold within them the potential for entire solar systems, planets, and perhaps even life. Now, consider for a moment what it would be like to stand inside one of these molecular clouds. You would see almost nothing. The dust is so thick, so finely distributed throughout the gas, that visible light from nearby stars cannot penetrate more than a fraction of the distance through it. You would be surrounded by a darkness deeper than any night on Earth. A darkness not of emptiness but of fullness, of matter so spread out that each cubic centimeter might contain only a few hundred or a few thousand molecules, impossibly thin by earthly standards, but stretching across such incomprehensible distances that the total mass becomes staggering. A single giant molecular cloud can contain the mass of 1 million suns, perhaps 10 million, all in the form of this cold, diffuse gas and dust. And yet the cloud does not immediately collapse. There are forces holding it up, resisting gravity's slow pull. Thermal pressure from the tiny amount of heat within the gas pushes outward. Magnetic fields thread through the cloud, adding structural support like invisible scaffolding. And turbulence, chaotic, swirling motions within the gas, stirs the cloud and prevents it from settling. For millions of years, these forces can hold the cloud in a delicate equilibrium, a balance between the urge to collapse and the resistance to do so. Astronomers sometimes call this a state of marginal stability. The cloud is poised, like a stone balanced on the edge of a hill. It needs only a nudge, and that nudge can come from many directions. Perhaps a nearby star explodes as a supernova, sending a shockwave rippling through the surrounding space, compressing the gas as it passes. Perhaps two molecular clouds drift into one another, their combined gravity overwhelming the internal resistance. Perhaps the spiral arm of a galaxy rotates past, creating a density wave that squeezes the cloud just enough. Whatever the trigger, the result is the same. Somewhere within the cloud, a region of gas becomes just dense enough that gravity gains the upper hand. And once that happens, there is no going back. The collapse has begun. Slowly, imperceptibly, matter begins to fall inward, gathering speed and density, and something new begins to take shape in the darkness. The first stage of a star's birth is known as gravitational fragmentation. When a region of a molecular cloud begins to collapse, it does not fall inward as a single, uniform mass. Instead, it breaks apart into smaller, denser clumps, each one a seed of a potential star. This happens because the collapsing gas is not perfectly uniform. There are slight variations in density from place to place, and as the overall cloud contracts, these slight irregularities become amplified. Denser patches pull in more material from their surroundings, growing heavier and more compact, while less dense regions are left behind. The British physicist Sir James Jeans first described this process mathematically in the early 20th century, calculating the minimum mass and size a cloud region must have before gravity can overwhelm its internal pressure. This threshold is now called the Jeans mass and the Jeans length, and they depend on the temperature and density of the gas. The colder and denser the gas, the smaller the fragment that can collapse under its own gravity. In the coldest cores of molecular clouds, where temperatures hover around 10 kelvins, the Jeans mass can be as low as a fraction of our Sun's mass. Each collapsing fragment is called a dense core, and it is within these cores that the next extraordinary chapter unfolds. As the core contracts, the gas at its center becomes denser and warmer. The gravitational energy of the infalling material is converted into heat, and the temperature at the heart of the core begins to rise. At first, this heat can escape in the form of infrared radiation, slipping out through the still relatively transparent outer layers of the core. But as the core grows denser, it becomes opaque, trapping the heat inside, and the temperature rises more rapidly. This is a critical transition. The core has shifted from an isothermal collapse, where the temperature remained roughly constant, to an adiabatic one, where the temperature climbs with the increasing pressure. At the very center of the core, a small, hot, dense object begins to form. It is not yet a star. It does not yet shine with the light of nuclear fusion. But it is something wonderful and new. It is called a protostar, and it is the first recognizable ancestor of every sun that has ever warmed a world. A protostar is a patient thing. It does not burst into existence in a flash of light. It grows slowly, sometimes over hundreds of thousands of years, as material from the surrounding dense core continues to rain down upon it. This process is called accretion, and it is both gentle and relentless. Gas and dust spiral inward, drawn by the protostar's growing gravitational pull, forming a flattened, rotating disk around the young object. This disk, known as a protoplanetary disk or sometimes a proplyd, is itself a marvel. It can extend for hundreds of astronomical units from the protostar, an astronomical unit being the distance from the Earth to our Sun, roughly 150 million kilometers. Within this disk, the seeds of future planets, moons, and asteroids are already beginning to gather. But we are getting ahead of ourselves. For now, our concern is the protostar at the center of it all. As it accumulates mass, its core temperature continues to climb. At around 2000 kelvins, the hydrogen molecules in the core, which until this point have been molecular hydrogen, two atoms bonded together, begin to dissociate, breaking apart into individual atoms. This dissociation absorbs energy, and it triggers a brief but dramatic second collapse of the core, compressing it further and raising the temperature even higher. The protostar is now a dense, hot ball of mostly hydrogen gas, perhaps a few times the radius of our Sun, but not yet hot enough at its center to ignite nuclear fusion. It is luminous, yes, but its light comes not from fusion, but from the enormous gravitational energy being released as material falls inward and compresses. This energy radiates outward, mostly in infrared wavelengths, invisible to our eyes but detectable by instruments like the James Webb Space Telescope, which has in recent years revealed protostars hidden deep within nebulae that were previously opaque to observation. The protostar continues to contract and heat. It may take another 10 million years, perhaps longer, before the temperature at its core reaches the critical threshold. But the process, once started, does not easily stop. Gravity is patient, and gravity is persistent, and the protostar is slowly, inevitably, approaching the moment when it will become a true star. Let us pause here for a moment and consider the sheer scale of time involved. When we say that a protostar may take 10 million years to reach the ignition point for nuclear fusion, it is easy for that number to wash over us, to be acknowledged without truly being felt. So let us try to feel it. 10 million years ago on Earth, the Miocene epoch was drawing toward its close. The Himalayas were still rising. The Mediterranean Sea had recently refilled after a dramatic period of near-complete evaporation known as the Messinian salinity crisis. Great apes were diversifying across Africa and Eurasia, and the ancestors of modern humans were still millions of years away from walking upright on the savannas. All of that, the mountains, the seas, the slow branching of our family tree, fits comfortably within the time it takes a single protostar to begin fusing hydrogen. And this is not an unusually long process by cosmic standards. It is, in fact, rather quick. Larger protostars, those destined to become massive, luminous giants, can reach fusion ignition in as little as 100,000 years, because their greater mass compresses the core more rapidly. But smaller protostars, those with masses well below that of our Sun, may take 100 million years or more. During all of this time, the protostar is evolving. It is shrinking, growing denser, growing hotter. It moves through what astronomers call the Hayashi track on the Hertzsprung-Russell diagram, a plot that maps stars according to their luminosity and surface temperature. The protostar begins large and cool and very luminous, radiating the energy of its contraction, and it gradually contracts and heats, sliding downward and to the left on the diagram. It is a slow, graceful descent toward the moment of ignition. And throughout this descent, the protostar is surrounded by the remnants of its birth cloud, still feeding on infalling gas, still wrapped in dust and mystery. It is hidden from visible light telescopes, a secret wrapped in silence, detectable only in infrared and radio wavelengths, a warm whisper in the cold dark. Then, at last, something miraculous happens. Deep in the heart of the protostar, where the temperature has been climbing for millions of years, the core reaches approximately 10 million kelvins. At this extraordinary temperature, hydrogen nuclei, bare protons, stripped of their electrons by the intense heat, are moving so fast that when they collide, they can overcome the electromagnetic repulsion that normally keeps them apart. They fuse. Two protons come together, and through a series of reactions, known as the proton-proton chain, they are gradually transformed into a nucleus of helium-4, releasing a small but significant amount of energy in the process, in the form of gamma-ray photons and tiny, nearly massless particles called neutrinos. This is nuclear fusion, and it is the process that powers every star in the observable universe. The energy released by a single fusion reaction is minuscule, far too small to warm a cup of tea. But in the core of a star, trillions upon trillions of these reactions are occurring every second, and the cumulative energy output is staggering. Our own Sun, a modest, middle-aged star of average mass, converts approximately 620 million metric tons of hydrogen into helium every second. In doing so, it loses roughly 4 million metric tons of mass, which is transformed into pure energy according to Einstein's famous equation, E = mc². That lost mass becomes the sunlight that warms our world, the light that sustains every green leaf, every ocean current driven by solar heating, every breath of wind. The ignition of fusion marks the moment when the protostar becomes a true star, joining what astronomers call the main sequence, the broad band of stars on the Hertzsprung-Russell diagram, where hydrogen fusion in the core is the primary energy source. Our Sun has been on the main sequence for approximately 4.5 billion years and is expected to remain there for roughly another 5 billion. It is, in a sense, in the long, stable middle chapter of its life, a chapter that began in the silent heart of a nebula so very long ago. Not all stars are born equal. The mass of the original dense core, the fragment of the molecular cloud that collapsed to form the protostar, determines almost everything about the star's future. It determines how hot the star will burn, how brightly it will shine, what color it will appear, and how long it will live. Stars less than about 8% of the Sun's mass never reach the temperatures needed to fuse hydrogen in their cores. These objects, known as brown dwarfs, are sometimes called failed stars, though that name does them a disservice. They are fascinating objects in their own right, glowing dimly in infrared light, slowly cooling over billions of years, occupying a strange and beautiful middle ground between the largest planets and the smallest stars. Stars with masses similar to our Sun, roughly between half and twice the Sun's mass, burn steadily for billions of years, fusing hydrogen into helium at a moderate pace. They are warm, yellow or orange, and they are among the most common types of stars in the Milky Way. Our galaxy alone is estimated to contain between 100 billion and 400 billion stars, and a significant fraction of these are Sun-like stars or smaller, cooler red dwarfs. And then there are the massive stars, those born with 10, 20, 50, or even more than 100 times the mass of our Sun. These are the blue giants and supergiants, and they are the most luminous, most dramatic, and most short-lived stars in the universe. A star 50 times the mass of the Sun may shine 1,000,000 times more brightly, but it will exhaust its hydrogen fuel in just a few million years, compared to the roughly 10 billion years allotted to a star like ours. The most massive stars live fast, burn fiercely, and die in some of the most violent events the cosmos has to offer. And yet, as we shall see, their deaths are not endings, they are beginnings. For in their deaths, they scatter the very elements that will seed the next generation of nebulae, the next generation of stars, and perhaps the next generation of worlds. Let us return for a time to the nebulae themselves, for they are not merely factories for stars. They are among the most beautiful objects in the known universe, and they come in many forms, each with its own character and its own story. The emission nebulae are perhaps the most visually striking. These are regions of ionized gas, heated and illuminated by the ultraviolet radiation of young hot stars embedded within them. The atoms of the gas, primarily hydrogen, but also oxygen, nitrogen, and sulfur, absorb this radiation and re-emit it at specific wavelengths, producing the vivid reds, blues, and greens that make emission nebulae so spectacular in astronomical images. The Orion Nebula, located roughly 1,340 light-years from Earth, is perhaps the most famous example. Visible to the naked eye as a faint smudge in the sword of the constellation Orion, it is a vast stellar nursery approximately 24 light-years across, containing enough material to form many thousands of stars. The Hubble Space Telescope and the James Webb Space Telescope have both produced extraordinary images of the Orion Nebula, revealing intricate structures of gas and dust, protoplanetary disks around young stars, and powerful jets of material being ejected from protostars at speeds of hundreds of kilometers per second. Then, there are the reflection nebulae, which do not emit their own light, but instead shine by reflecting the light of nearby stars, much as a cloud on Earth might glow silver white in the light of a full moon. Reflection nebulae tend to appear blue because shorter wavelengths of light are scattered more efficiently by the fine dust particles within them, a phenomenon related to the same Rayleigh scattering that makes our own daytime sky blue. The Pleiades star cluster, also known as the Seven Sisters, is surrounded by a beautiful reflection nebula, its blue haze a reminder that even the spaces between stars can hold a quiet, borrowed luminosity. And then there are the planetary nebulae, which, despite their misleading name, have nothing to do with planets at all. The name was coined in the 18th century by the astronomer William Herschel, who thought that their round, greenish appearance through his telescope resembled the disk of a planet. In reality, a planetary nebula is the glowing shell of gas expelled by a dying low to intermediate mass star. A star not massive enough to explode as a supernova, but one that, in the final stages of its life, sheds its outer layers into space in a series of gentle but immense exhalations. At the center of a planetary nebula lies the exposed core of the dead star, a small, incredibly dense object called a white dwarf. The white dwarf is roughly the size of Earth, but contains a mass comparable to that of the Sun, giving it a density so extreme that a teaspoon of white dwarf material would weigh several tons. The white dwarf is intensely hot, sometimes reaching surface temperatures of over 100,000 kelvins, and its fierce ultraviolet radiation illuminates the expanding shell of gas around it, causing it to glow in the ethereal colors that make planetary nebulae so hauntingly beautiful. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco, these are among the most photographed and studied planetary nebulae, each one a unique sculpture of light and gas, shaped by the complex interactions between the expelled material and the radiation of the central white dwarf. They are, in a sense, monuments to stars that have lived and died. And within their expanding shells, enriched with carbon, nitrogen, and oxygen forged in the star's interior during its lifetime, they carry the elements that will eventually mix back into the interstellar medium, joining the vast reservoir of gas and dust from which new molecular clouds, new protostars, and new stars will one day form. The cycle, you see, is never truly broken. Perhaps the most spectacular of all nebulae are the supernova remnants, the vast expanding clouds of debris left behind when a massive star reaches the end of its life and explodes. A core collapse supernova occurs when a star of roughly 8 or more solar masses exhausts the nuclear fuel in its core. Throughout its life, such a star fuses progressively heavier elements, hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. But iron is the end of the line. Fusing iron does not release energy, it absorbs it. And so, when the core of the massive star becomes a ball of iron, roughly the mass of our Sun, compressed into a sphere no larger than Earth, the fusion reactions that have supported the star against its own gravity for millions of years suddenly cease. In less than a second, the iron core collapses. It falls inward at speeds approaching a quarter of the speed of light, compressing to densities so extreme that protons and electrons are forced together to form neutrons. The collapsing core rebounds off this incompressible neutron matter, and the resulting shockwave, amplified by a flood of neutrinos from the core, tears the star apart. The explosion is beyond comprehension. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The energy released is approximately 10 to the power of 46 joules, more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. And the debris, enriched with every element on the periodic table, including heavy elements like gold, platinum, and uranium, forged in the extreme conditions of the explosion itself, is flung outward into space at thousands of kilometers per second. Over thousands of years, this debris expands and cools, forming the beautiful, filamentary structures we see as supernova remnants. The Crab Nebula, the remnant of a supernova observed by Chinese and possibly other astronomers in the year 1054, is one of the most studied objects in the sky. And at its center lies a pulsar, a rapidly spinning neutron star, the collapsed core of the original star, spinning roughly 30 times per second and emitting beams of radiation like a cosmic lighthouse. And here, perhaps, is the most beautiful truth in all of stellar astronomy. The debris from supernova explosions, the carbon, the oxygen, the silicon, the iron, the calcium, does not simply vanish into the void. It mingles with the existing interstellar medium, enriching the vast clouds of hydrogen and helium that drift between the stars. Over millions of years, these enriched clouds gather, cool, and condense, forming new molecular clouds, new dense cores, new protostars, And the stars that are born from these enriched clouds contain not only hydrogen and helium, but also the heavier elements forged in the hearts and deaths of earlier generations of stars. Our own Sun is what astronomers call a population 1 star, meaning it is relatively rich in heavy elements, sometimes called metals in the astronomical sense of the word. This tells us that our Sun was born from material that had already been processed through at least one, and probably several, previous generations of stars. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, as you listen to these words, all of it was forged inside a star that lived and died before our Sun was born. This is not metaphor. This is not poetry dressed as science. This is literal, measurable, chemical fact. The astronomer Carl Sagan expressed it most beautifully when he said that we are made of star stuff. Every atom heavier than hydrogen and helium in your body has a stellar ancestry. Some of those atoms may have been forged billions of years ago, in stars that existed in the early epochs of our galaxy's history, stars whose light has long since faded, but whose material legacy persists in every rock, every ocean, every living thing on Earth. The nebulae, then, are not merely astronomical objects. They are the links in an unbroken chain of creation that stretches from the first stars to the present moment, a chain in which destruction is always followed by renewal, and death is always the prelude to birth. There is one more type of nebula worth pausing to appreciate, one that speaks to the universe's quieter, more contemplative side. These are the dark nebulae, clouds of gas and dust, so dense and so cold that they block virtually all light from passing through them. They appear as inky silhouettes against the brighter backdrop of the Milky Way, or against more luminous nebulae behind them. The astronomer Edward Emerson Barnard catalogued many of these dark nebulae in the early 20th century, and they are still known today by their Barnard numbers. Barnard 68, for example, is a small, roughly spherical dark nebula located about 500 light-years from Earth. In visible light images, it looks like a hole in the starfield, a region of absolute darkness surrounded by thousands of stars. But in infrared, the stars behind it become visible. Their light reddened and dimmed by the dust, but not entirely blocked. Dark nebulae are among the coldest objects in the galaxy, with internal temperatures as low as 6 to 10 kelvins. They are also among the densest parts of molecular clouds, and many of them are thought to be in the early stages of gravitational collapse, harboring within them the seeds of future protostars. The Coalsack Nebula, visible as a dark patch in the Southern Cross, was known to indigenous Australians for thousands of years, woven into their rich astronomical traditions. The Horsehead Nebula in Orion, perhaps the most iconic dark nebula of all, is a pillar of cold dust rising against the glowing red backdrop of an emission nebula, sculpted by the radiation of nearby hot stars into a shape that, with a little imagination, resembles the head of a horse. These dark nebulae remind us that absence can be as beautiful as presence, that silence can be as eloquent as sound. In the vast tapestry of the cosmos, the dark spaces are not empty. They are full of potential, full of matter waiting for the slow, inevitable call of gravity to begin the process of creation once more. In recent decades, our ability to observe nebulae and the star formation process has been transformed by new generations of telescopes. The Hubble Space Telescope, launched in 1990, gave us some of the most iconic images of nebulae ever captured, including the famous Pillars of Creation in the Eagle Nebula, towering columns of gas and dust several light-years tall, within which new stars are actively forming. The Spitzer Space Telescope, which observed in infrared wavelengths, allowed astronomers to peer through the dust that obscures so much of the star formation process from visible light telescopes, revealing hidden protostars and the intricate structures of molecular clouds. And the James Webb Space Telescope, launched in December of 2021, has taken these observations to an entirely new level. With its unprecedented sensitivity in infrared wavelengths, Webb has revealed details within nebulae that were previously invisible: the earliest stages of protostellar collapse, the complex chemistry of protoplanetary disks, and the influence of young massive stars on their surrounding environments. Webb's image of the Carina Nebula, released in July of 2022, as one of the telescope's first full-color images, showed a landscape of cosmic cliffs and valleys sculpted by the radiation and stellar winds of massive young stars. A scene of such breathtaking beauty and complexity that it seemed almost impossible that it was real. Radio telescopes, too, have played a crucial role. The Atacama Large Millimeter Array, known as ALMA, located in the high desert of northern Chile, observes at millimeter and submillimeter wavelengths, allowing it to detect the cold molecular gas in the densest parts of molecular clouds. ALMA has produced remarkable images of protoplanetary disks, revealing rings and gaps that suggest planets may already be forming within them. Together, these instruments have given us a picture of star formation that is richer, more detailed, and more beautiful than anything previous generations of astronomers could have imagined. And yet, there remains so much we do not know. The precise mechanisms that trigger the initial collapse of a molecular cloud core, the role of magnetic fields in regulating the process, the details of how planetary systems emerge from protoplanetary disks. These are among the most active and exciting areas of research in modern astrophysics. You lie here tonight, breathing slowly, feeling the gentle pull of sleep beginning to gather at the edges of your awareness. Consider this. Somewhere in our galaxy, right now, at this very moment, a star is being born. In some cold, dark corner of a molecular cloud, a dense core is quietly collapsing, its temperature rising, its destiny taking shape in the silence. We cannot see it. It is hidden behind curtains of dust, radiating only in wavelengths our eyes cannot detect. But it is there. And somewhere else, another star is dying, shedding its outer layers in a gentle exhalation, or tearing itself apart in a cataclysmic explosion, scattering the elements it forged over millions or billions of years back into the interstellar medium. These processes are happening continuously, everywhere, across the hundreds of billions of galaxies in the observable universe. The cycle of stellar birth and death is not an event that happened once in the distant past. It is a living, ongoing process, as natural and as constant as the tides on Earth or the turning of the seasons. And we are part of it, not merely as observers, but as participants. The atoms that compose your body were once inside a nebula. They were once part of a collapsing dense core, then part of a protostar, then part of a fully formed star. They may have been expelled in a supernova, drifted through interstellar space for millions of years, and eventually found their way into the molecular cloud that gave birth to our sun and our solar system, roughly 4.5 billion years ago. You are not separate from the cosmos. You are the cosmos, rearranged into a form that can lie in the dark and wonder about its own origins. And that, perhaps, is the most beautiful part of the story. The universe is not merely something we observe from the outside. It is something we are woven into, at the deepest atomic level, a tapestry of matter and energy that has been creating and recreating itself for nearly 14 billion years. Consider for a moment the sheer patience of the universe. A molecular cloud may drift through the galaxy for tens of millions of years before something stirs it into creation. It may be the shockwave from a distant supernova, rippling outward at thousands of kilometers per second, compressing the gas it encounters like a hand pressing slowly into soft clay. Or it may be the gentle gravitational tug of a passing star, whose influence, though subtle, is enough to nudge a region of the cloud past a critical threshold of density. Scientists call this the Jeans instability, named after the British physicist Sir James Jeans, who in the early 20th century described the conditions under which a cloud of gas will collapse under its own gravity rather than remain dispersed. When the mass within a given volume exceeds what is known as the Jeans mass, gravity wins its quiet war against thermal pressure, and the cloud begins to fall inward. There is no explosion, no dramatic flash. The collapse is extraordinarily slow by human standards, unfolding over perhaps 100,000 years. And yet, by cosmic reckoning, it is remarkably swift. Within that contracting region, the gas grows warmer as gravitational potential energy converts to heat, and the core becomes denser and more opaque. This is the moment a protostar is born. Though it will not yet shine with the light of nuclear fusion, it glows instead with the heat of its own compression, a dim ember buried deep within a cocoon of dust, invisible to ordinary telescopes but radiant in the infrared. The Spitzer Space Telescope, which operated from 2003 to 2020, revealed thousands of these hidden protostars nestled inside dark clouds throughout our galaxy. Each one a promise, each one a beginning. And around each collapsing core, the remaining gas and dust do not simply fall straight in. Because the original cloud possessed even the faintest rotation, conservation of angular momentum causes the infalling material to flatten into a spinning disk, a structure that will one day give rise to planets, moons, and perhaps, in some unimaginably distant future, beings who will look up and wonder where they came from. That spinning disk of gas and dust, known as a protoplanetary disk, is one of the most elegant structures in all of astrophysics. It can stretch across hundreds of astronomical units, where one astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. Within this vast, flattened expanse, particles of dust no larger than grains of sand begin to collide and cling together, a process called accretion. Over hundreds of thousands of years, those grains become pebbles, those pebbles become boulders, and those boulders become planetesimals, objects perhaps a kilometer across. And all of this unfolds in near silence, in the cold vacuum surrounding a star that has not yet fully ignited. Meanwhile, at the center of the disk, the protostar continues to grow. It pulls material from its surroundings through the disk itself, feeding steadily, growing hotter and denser with each passing millennium. Some of that infalling material does not reach the star at all, but is instead redirected along powerful magnetic field lines and launched outward in narrow, high-speed jets that can extend for light years in both directions. These bipolar outflows, as astronomers call them, are among the most striking signatures of young stellar objects. The Hubble Space Telescope has captured breathtaking images of these jets, known as Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them independently in the 1950s. The jets glow where they collide with surrounding interstellar gas, creating luminous bow shocks shaped like the prow waves of a ship cutting through still water. And so the young star announces itself, not with a sudden blaze of light, but with these twin beams of energy reaching out into the darkness, parting the cloud from which it was born. There is something profoundly moving about this image. A star not yet fully formed, already reshaping its environment, already influencing the space around it. It reminds us, perhaps, that even the smallest beginnings carry within them the power to change what surrounds them, gently, persistently, across spans of time we can barely begin to imagine. There comes a moment, deep within the contracting core of a protostar, when the temperature reaches approximately 10 million degrees Kelvin. At this extraordinary threshold, hydrogen nuclei, which are simply individual protons, begin to move fast enough to overcome their mutual electromagnetic repulsion and fuse together. This is the proton-proton chain reaction, the same process that powers our own sun, and it marks the true birth of a star. When fusion ignites, the outward pressure of the energy it releases finally balances the inward pull of gravity, and the star settles into a state of equilibrium known as hydrostatic balance. It will remain in this delicate state for millions or even billions of years, depending on its mass. A star like our Sun, a modest yellow dwarf, will burn steadily on the main sequence for roughly 10 billion years. A massive blue giant, perhaps 30 or 40 times the Sun's mass, will consume its fuel in a mere few million years, blazing with furious brilliance before meeting a dramatic end. And a small red dwarf, the most common type of star in the galaxy, may burn so slowly and so efficiently that it persists for trillions of years, far longer than the current age of the universe, which is approximately 13.8 billion years. No red dwarf that has ever formed has yet had time to die. They are all still burning, every single one of them, the oldest among them lit in the earliest epochs of the cosmos, still glowing faintly in the darkness. There is something deeply comforting in that thought, that the smallest, most humble stars are also the most enduring, that patience and modesty, even in the physics of stellar evolution, carry their own quiet rewards. And so, the nebula's work is done. Where once there was only cold, diffuse gas, now there is light. Where once there was silence, now there is the steady, almost imperceptible hum of nuclear fusion, a sound no ear will ever hear, but a warmth that will sustain worlds for eons yet to come. But the story does not end when a star is born, for nebulae are not merely cradles. They are also, in time, the resting places to which stars return. When a star like our Sun reaches the end of its life, it swells into a red giant, shedding its outer layers in gentle pulses that drift outward into space, forming what we call a planetary nebula, a name that has nothing to do with planets, but was given in the 18th century by William Herschel, who thought these round, glowing shells resembled the disks of distant worlds through his telescope. The Ring Nebula in the constellation Lyra is one such remnant, a delicate hoop of ionized gas, glowing in shades of blue, green and red, surrounding the tiny, intensely hot white dwarf that remains at its center. And when a far more massive star exhausts its fuel, the result is vastly more dramatic. The core collapses in a fraction of a second, and the outer layers are hurled outward in a supernova explosion, one of the most energetic events in the known universe. The Crab Nebula in Taurus is the remnant of such an explosion, recorded by Chinese and possibly Arab astronomers in the year 1054. At its heart spins a pulsar, a neutron star, rotating roughly 30 times per second, sending beams of radiation sweeping across space like a cosmic lighthouse. The material flung outward by supernovae enriches the surrounding interstellar medium with heavy elements, carbon, oxygen, iron, gold, elements that were forged in the furnaces of stellar cores and in the cataclysmic seconds of the explosion itself. These elements mix with existing hydrogen and helium, seeding the next generation of molecular clouds, the next generation of collapsing cores, the next generation of stars and planets. And so the cycle continues, each generation of stars building upon the ashes of the last, an endless, quiet recursion of creation and dissolution. The calcium in your bones, the iron in your blood, the oxygen filling your lungs with each slow, drowsy breath you take tonight, all of it was once inside a star. All of it passed through a nebula. You are, quite literally, stardust resting upon stardust. When a massive young star ignites within the heart of a nebula, it does not simply glow in quiet gratitude. It roars, silently, with ultraviolet radiation so intense that it begins to reshape the very cloud from which it was born. This process, known as photoionization, strips electrons from hydrogen atoms across vast distances, causing the surrounding gas to fluoresce in hues of crimson, rose, and soft coral. These are the emission nebulae, the glowing cathedrals of ionized hydrogen that we see in some of the most celebrated images ever captured by telescopes. The Orion Nebula, located roughly 1,340 light-years from Earth, is perhaps the most famous of these luminous nurseries. Its central region, sculpted by a cluster of hot young stars known as the trapezium. And yet the influence of a newborn star extends far beyond mere illumination. The fierce stellar winds that pour outward from its surface, sometimes at speeds exceeding 2,000 kilometers per second, push against the surrounding molecular gas, compressing it, sweeping it into dense shells and pillars. These winds carve cavities within the nebula, hollowing out vast bubbles of hot, tenuous plasma surrounded by walls of cooler, denser material. In this way, the star simultaneously destroys part of the cloud and, through compression, encourages new regions of collapse elsewhere. It is a paradox written in light and pressure, a cycle in which creation and erosion are not opposites, but partners in the same slow choreography. Consider the famous pillars of creation within the Eagle Nebula, roughly 6,500 light-years away. Those towering columns of gas and dust, some stretching 4 or 5 light-years in length, are being sculpted by the radiation of nearby O-type stars, the hottest and most luminous class. Even as the pillars are gradually being eroded, evaporating grain by grain into the surrounding void, their dense interiors may still harbor collapsing cores, new protostars forming within structures that are themselves dissolving. There is something profoundly poetic in this, something that speaks to the nature of impermanence itself, how even the act of disappearing can be an act of giving birth. Not all nebulae glow with their own emitted light. Some shine only because they are near enough to a bright star to reflect its radiance, scattering shorter wavelengths of light preferentially, much as Earth's atmosphere scatters sunlight to paint the sky blue. These are the reflection nebulae, and they tend to appear in soft, cool tones of cerulean and periwinkle, a gentle contrast to the warm reds of their emission cousins. The nebula surrounding the Pleiades star cluster, that delicate gathering of young blue stars roughly 440 light-years distant, is one of the finest examples. Thin veils of interstellar dust catch the starlight and diffuse it into a hazy blue glow that seems almost painted by hand. And then there are the dark nebulae, regions so dense with dust that they block the light of everything behind them, appearing as silhouettes against brighter backgrounds. The Horsehead Nebula in the constellation Orion is perhaps the most iconic, a column of cold, opaque dust shaped by chance and erosion into a form that resembles an equine profile. These dark clouds are not empty voids, but among the densest and coldest regions of the interstellar medium, often with temperatures as low as 10 kelvins, just 10 degrees above absolute zero. Within them, molecules form that cannot survive in warmer, more exposed environments. Complex molecules of carbon, nitrogen, and oxygen bonded with hydrogen, including some that are precursors to the organic chemistry of life. It is a humbling thought that the cold, dark places of the cosmos, the places where no light escapes and no warmth intrudes, may be among the most chemically creative. Somewhere inside a dark nebula, in conditions that would seem utterly hostile to anything we associate with vitality, the molecular building blocks of amino acids and sugars are slowly assembling, drifting on currents of gravity and magnetic fields, waiting for the day when a collapsing core will gather them into a protoplanetary disk and, eventually, perhaps, onto the surface of a world. The darkness, it turns out, is not the absence of possibility. It is the quiet workshop where possibility is being prepared. There is another kind of nebula, one born not from the slow accumulation of interstellar material, but from the death of a star. When a star of roughly 1 to 8 solar masses exhausts the hydrogen and helium fuel in its core, it swells into a red giant and then, in its final chapters, gently sheds its outer layers into space. These expanding shells of gas, illuminated by the exposed, intensely hot remnant core at the center, are called planetary nebulae, a name that is something of a historical accident. When the astronomer William Herschel observed them in the late 18th century, their round, greenish disks reminded him of the planet Uranus, which he himself had discovered in 1781. The name persisted, even though these objects have nothing whatsoever to do with planets. Planetary nebulae are among the most visually stunning structures in the cosmos. The Ring Nebula in the constellation Lyra, roughly 2,300 light-years away, glows in concentric layers of blue, green, and red, each color corresponding to a different ionized element. Oxygen closer to the center, hydrogen and nitrogen farther out. The Cat's Eye Nebula, studied in extraordinary detail by the Hubble Space Telescope, reveals intricate nested shells and jets that suggest a complex history of episodic mass ejection. These dying exhalations of aging stars are not merely beautiful. They are essential to the chemical evolution of the galaxy. Throughout their lifetimes, stars fuse lighter elements into heavier ones, carbon from helium, nitrogen and oxygen from carbon, and when they shed their outer envelopes, they return those enriched materials to the interstellar medium. The next generation of nebulae, the next generation of stars and planets, will inherit this enriched legacy. Every carbon atom in your body, every oxygen atom you breathe, was forged inside a star and expelled into space by a process much like this. Planetary nebulae are, in a very real sense, the generous last gifts of stars that have spent their fuel, the quiet bequeathing of complexity to a universe that hungers for it. Then there are the nebulae born from violence, the supernova remnants, the expanding debris fields of stars that were too massive to die gently. When a star exceeding roughly 8 solar masses reaches the end of its fuel, its core collapses in a fraction of a second, and the resulting shockwave tears the rest of the star apart in an explosion so luminous that it can, for a few weeks, outshine an entire galaxy of hundreds of billions of stars. The material flung outward in that detonation races into the surrounding interstellar medium at thousands of kilometers per second, heating and compressing everything it encounters, creating vast, filamentary structures of superheated gas that can persist for tens of thousands of years. The Crab Nebula, located roughly 6,500 light-years away in the constellation Taurus, is the remnant of a supernova that was observed by Chinese and possibly other astronomers in the year 1054. At its center lies a rapidly spinning neutron star, a pulsar, rotating approximately 30 times per second and emitting beams of radiation that sweep across space like a cosmic lighthouse. The Veil Nebula in Cygnus, a delicate lacework of shock-heated filaments, is the remnant of a star that exploded perhaps 10 to 20,000 years ago, its expanding shell now spanning nearly 3 degrees of the night sky. Supernova remnants are the universe's great recyclers, and they contribute something that planetary nebulae alone cannot. The immense energies of the explosion drive nucleosynthesis beyond what ordinary stellar fusion achieves, creating elements heavier than iron, gold, platinum, uranium, elements forged in the seconds of the explosion itself. These heavy elements are scattered across light years, seeding future molecular clouds with the raw materials for rocky planets, and ultimately, the intricate biochemistry of living things. So when you rest tonight, consider that the iron in your blood was produced in the final moments of a star that died long before the sun was born, flung across space in a supernova remnant that drifted, cooled, mingled, and eventually collapsed to form the nebula from which our own solar system arose. Within these vast nurseries of gas and dust, the actual birth of a star begins with an event so quiet, so imperceptibly gentle, that no instrument could ever hope to witness the precise moment it starts. Somewhere deep inside a molecular cloud, a region of slightly higher density begins to attract the material around it through the patient, tireless pull of gravity. Perhaps a shockwave from a nearby supernova nudges a pocket of gas just enough, or the slow rotation of the galaxy compresses one edge of the cloud as it drifts along a spiral arm. Whatever the trigger, the result is the same. A gradual gathering, a quiet collapse inward, as billions upon billions of hydrogen molecules begin their long, unhurried fall toward a common center. This collapsing region is called a protostellar core, and in its earlier stages, it is remarkably cold, perhaps only 10 degrees above absolute zero, colder than any winter night you have ever known or could ever imagine. And yet, as gravity draws the material inward, something begins to change. The gas compresses, and as it compresses, it warms. This is a fundamental principle of physics. When you squeeze a gas into a smaller volume, its temperature rises. The molecules collide more frequently, more energetically, and the core begins to glow faintly in the infrared. Invisible to our eyes, but detectable by telescopes like the James Webb Space Telescope, which peers through the dust to find these hidden embryos of light. Over tens of thousands of years, the collapsing cloud flattens into a spinning disk of material, a structure astronomers call an accretion disk. At its center, the protostar continues to grow, pulling in matter from the disk like water, spiraling slowly down a drain. The temperature at the core climbs steadily, from hundreds of degrees to thousands to tens of thousands, and still it is not yet a star. It is a promise of a star, a seed buried in darkness, gathering the warmth and pressure it will need to ignite. The universe, as always, is patient, and this particular act of creation cannot be rushed. The moment a protostar truly becomes a star is defined by a single extraordinary threshold, the ignition of nuclear fusion at its core. For this to happen, the temperature at the center of the collapsing cloud must reach approximately 10 million degrees Celsius. At that unimaginable heat, hydrogen nuclei move so fast, collide with such force, that they overcome the electromagnetic repulsion that normally keeps them apart, and they fuse together to form helium. Each fusion event releases a tiny burst of energy, but when trillions upon trillions of these reactions occur every second, the result is a sustained, radiant outpouring of light and heat, the engine that will power the star for millions or even billions of years to come. This process, called the proton-proton chain in stars like our Sun, converts roughly 4 million metric tons of matter into pure energy every single second, following the relationship described by Einstein's famous equation relating energy to mass and the speed of light. And yet, the star does not explode from all this fury. It achieves a delicate, beautiful equilibrium known as hydrostatic balance, where the outward pressure of the radiation generated by fusion perfectly counteracts the inward crush of gravity. It is a balance as elegant as anything in nature. Two immense forces holding each other in check, and the star hanging there between them, luminous and stable. For a star like our Sun, this main sequence phase, this long quiet burning, will last approximately 10 billion years. Our Sun is roughly 4.5 billion years into that journey, a middle-aged star still burning steadily, still warming the inner planets of its system, with the light born from hydrogen becoming helium deep in its core. Consider, for a moment, the profound simplicity of it. That the light touching your face on a summer afternoon began as the collision of atoms at the heart of a furnace, 10 million degrees hot, traveled outward through the Sun's interior over thousands of years, and then crossed 150 million kilometers of empty space in just over 8 minutes to reach you. And so, as the nebulae continue their ancient, silent work far above, let yourself become still. Let the images of glowing gas and newborn stars soften and blur at the edges of your mind, the way distant galaxies blur at the edges of the observable universe. You do not need to hold on to any of this. The knowledge will be there when you wake. For now, there is only the gentle pull of sleep, drawing you inward, the way gravity draws a cloud of hydrogen toward its center. There is no hurry. There is no urgency. The stars have been forming for 13 billion years, and they will continue long after tonight as a memory. You are safe. You are warm. You are made of the same matter that fills the nebulae, and tonight, like a star still gathering itself in the darkness, you are simply resting, simply waiting, simply being. Let the silence hold you. Let the cosmos carry you gently into sleep. If this journey through the nebulae brought you a moment of peace tonight, consider leaving a gentle note in the comments about which part you remember most. And if you have not yet, subscribe so we can explore the cosmos together again tomorrow. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.